In this example, we calculate the actual vent Hoff factor for a salt solution from the osmotic pressure. Our problem reads, calculate the actual vent Hoff factor for an aqueous 8.00% by mass iron 3 chloride solution if its osmotic pressure is 46.2 atmospheres at 60.0 degrees Celsius. The density of the solution is 1.055 grams per milliliter. We can start with our equation for osmotic pressure, which equals the vent Hoff factor times molarity times the ideal gas law constant times temperature. Rearranging this equation, we can solve for the vent Hoff factor. To calculate molarity, we will need moles of iron 3 chloride per liter of solution. Since we're not given a quantity of solution in the problem, when converting from percent by mass to molarity, we can make one assumption about the amount of solution we're working with. Let's make the assumption based on the denominator of the units we're given. This will make the math easier. Since grams of solution are in the denominator for percent by mass, we can assume we have 100 grams of solution. If we have 100 grams solution, and 8.00% of the solution by mass is iron 3 chloride, then we have 8.00 grams of iron 3 chloride. We can convert grams iron 3 chloride to moles using dimensional analysis and the molar mass of iron 3 chloride. We should have 0.04932 moles iron 3 chloride. Then we can convert 100 gram solution into liters using the density of the solution in dimensional analysis. We should have 0.0948 liters solution. We can plug these values into our molarity equation, and we should see the solution is 0.5203 molar iron 3 chloride. And last of all, we can plug the molarity, given osmotic pressure and temperature, into the equation to solve for the vent Hoff factor. We need to remember to convert 60.0 degrees Celsius into Kelvin by adding 273.15. Completing the calculation, we get 3.25 as the actual vent Hoff factor. This seems to be a reasonable answer, since the ideal vent Hoff factor for iron 3 chloride would be 4.